Strong acids and bases are strong electrolytes that exist entirely as ions in aqueous solution. If you haven't already, you will want to memorize the names and formulas of the 7 strong acids. Sometimes I refer to them as the 7 dwarfs. And those 7 strong acids are hydrochloric, HCl, hydrobromic, HBr, hydroiodic, HI, chloric, HClO3, perchloric, HClO4, nitric, HNO3, and sulfuric, H2SO4. Besides hydrogen and oxygen, on the periodic table, you can see that chlorine is present in 3 of the strong acids, and then the other elements that are in each of the other 4 strong acids are shown here. There's nitrogen and sulfur and bromine and iodine. If you haven't already, make sure you memorize the names and formulas of the 7 strong acids. There are only 7. You'll also want to know what I call the strong base cations. Hydroxides of the strong base cations are strong bases. There are 8 of these, and I've colored them here on the periodic table for you. The hydroxides, that is, whenever any of these elements in the darkened region here are paired up with OH-, which is the hydroxide ion, that is a strong base. If you have a good visual sense, you can see that this darkened region is like a lowercase b, B for base. This element down here, francium, and this element right here, radium, we don't have too much interest in, so we kind of forget those. But these 8 metals, what I call the strong base cations, because when they're paired up with hydroxide ion, they make a strong base. Strong electrolytes are written using a one-sided arrow. Here's nitric acid. You can see the one-sided arrow. It ionizes 100% into H plus and NO3 minus. So let's try a problem by finding the pH of a 0.012 molar perchloric acid solution. So first of all, we need to know that perchloric acid is HClO4, and it ionizes 100% as follows. Now, to solve this problem, we don't actually have to write that down, but you at least have to think it. Because what this problem kind of says is that the concentration of the HClO4 is 0.012, but in reality, we know that because this is a strong acid, the concentration of HClO4 molecules in the solution is essentially 0, but that the concentration of the hydrogen ion and the perchlorate ion are both 0.012. Now, about the perchlorate ion concentration, who cares? Certainly Ron Swanson doesn't care, because that isn't going to affect the pH. What is going to affect the pH is the concentration of the hydrogen ion. So we're going to find the pH by taking the negative logarithm of the hydrogen ion concentration, and that gives us a pH of 1.92. And we would expect a pH less than 7 from an acid solution. Let's try one more. If a nitric acid solution has pH 2.66, find its concentration. Again, if we don't write this down, that's one thing, but we certainly have to think, oh, nitric acid is HNO3, it ionizes 100% to H plus and NO3 minus. And what we're asked is, what's the concentration of the HNO3? We know that in reality, there's virtually no HNO3 molecules that are intact. That is, neutral HNO3 molecules pretty much don't exist in this solution. But nonetheless, whenever we're asked to find the concentration of a nitric acid solution, that's the question that's being asked. So here's what we're going to do. We're going to calculate the hydrogen ion concentration by taking 10 to the negative pH, which gives us this value, 2.2 times 10 to the negative third molar. That's the concentration of hydrogen ion. It's also the concentration of nitrate ion in the solution. Well, if we were to go back and say, what would the concentration of the HNO3 have to be in order that the concentrations of hydrogen ion and nitrate ion were both 2.2 times 10 to the negative third? We would also say the nitric acid solution, therefore, is 2.2 times 10 to the negative third.